You already follow? It's called sepsis. All right? That's what it's called. You get toxin in the bloodstream. That's not good. Separate of the bacteria. Did everybody hear me? So if you start, so this is why you want to control it. This is why you want the macrophages and the neutrophils. Did everybody hear me? Because the macrophage will be like, yo, neutrophil, come on, man, come help me. Right?
Is there a vaccine for sepsis or like medicine?
No, because sepsis is a general term that any one of these and others, including the worms and the parasites, can lead you down. It's like anything that's foreign that gets brought into a sterile area and then into the bloodstream is going to lead to sepsis.
Because I've seen like commercials like, oh, your kid might have sepsis, but it's like, what do you do for it? Like,
you try to catch it early enough, and when the whole response, and hope that you can keep their fluid levels up and the temperature down. You know, I mean, guys, let's be honest, right? What's a real temperature? Anybody know? Please don't come to me with the 101. Please don't come to me with 102. Because I'm going to give the kid the medicine, but you know why? To placate mom. And that's what doctors do. Instead of telling mom, hey, you know what, 101, take him home. Be more at risk for getting sick here in the hospital, take him home. If it gets a little too hot, you know what? Throw him in the cold tub. Can't tolerate the cold tub? Hey man, I used to, every time I got a fever, I up the ante. I jump in a hot tub. How you like that?
For real, you would.
Yeah. Boy, my ass is gonna kill me. I'm gonna be just made stronger. Yeah, bacteria can't mess with me. Yeah.
What's the like temperature that would kill you if you take?
Yeah, it was 106. Then you're worried.
Because I went to the hospital at 105 point something.
Yeah. 105. We got you butt naked in an ice bath.
They just like connected me to an IV and that's it. Like,
yeah, they can do that too as an adult.
Yeah.
Yeah, because we got a big bathtub. You know. Yeah. No, what we do is we take your clothes off, and then we have thermal bags that they'll put that will actually pull the heat away from those particular areas. Mm-hmm. So they have bags that they can put you in and actually,
but they didn't
constantly circulate cool air across the body. Yeah. So just like they can heat it up for thermal bags, like if you've been stuck in cold for a long period of time. Not that that'll help because it's just
it's just the thing. About 2 when he had seizures at 102 for fever.
So you can. What happens is there's variation in humans. Most kids, 102 and epileptic seizures. That's not normal. That means he's already had a propensity for seizures.
That was the first time, and then after that they prescribed, like baby Motrin. He was not above that having a low fever. Yeah,
it's just his inability to.
He's never had a seizure.
Because of 102, yeah, but that I'm going to tell you that's at 102 you shouldn't be seeing seizures in a kid who has 102. You're seeing seizures in a kid at 102. That's an issue that's a genetic issue with certain things that are going on with that child. Each human is different, though. But each human is different. I mean, it is what it is. So there is a lot of variation in humans. So, all right. So let's finish this story. So the lysosome and the peroxisome, they come in with the phagosome. It now becomes a phagolysosome or phagolysoperoxisome. The whole idea is to digest everything. But once that's done, once that's all said and done, everybody got me? We now have what? Well, this progresses to now having all this processed antigen in it. Everybody see that? With epitopes. So you got the triangle, you got the circle, you got the square, and you got the star. Right? Not to exclude my Jewish people, right? Let's put a little Jewish star up in there too. Don't exclude my family of Jews, right? All right. So then now you got all these little particles on them with the epitopes that are on them for recognition. So the next step is, sure enough, because we're talking about macrophages and B cells, you're gonna have this vesicle that has an in it and on it, in the vesicle, it's got this MHC class 2 marker. This stuff will never get into cytoplasm. Did everybody hear me? None of that product should never get into the cytoplasm. Sure enough, spirochetes, atypical bacteria, they can avoid this whole capturing process and enter into the cytoplasm of the cell and cause cell destruction. And that's how they wreak havoc. So there are certain bacteria that can avoid the phagolysosome, guys. Did you hear me? I told you I was going to give you the skinny on microbiome, didn't I? Because I can't teach you immunology and not teach you about microbiology, at least to some extent. Everybody understand me so far? Yes.
So MHC2 that's exogenous, right?
Ah, did everybody hear what he just said?
Is that what you said?
MHC,
You said that.
no, you just said it. I didn't say it, you said it.
That's what you
I'm
said.
agreeing with you.
Okay.
You said it, not me. I didn't use the word exogenous. You
drew
used it.
inside
Yes.
of the macrophage.
He said everything that's outside the cell, even though it comes into the cell, stays what? Really outside the cytoplasm of the cell. This is how that process, this is called exogenous. It's the exogenous pathway. The endogenous pathway is protein from viral and cell that gets generated and put onto MHC class 1 via the ubiquitin proteasome complex. You got me? Now, the ubiquitin proteasome complex you may find in chapter 3, literally like maybe 1 or 2 sentences in the textbook about it. Okay? This is pathology. I'm teaching you pathology right now, a little bit of pathology right now. Because why? I can't teach you about immunology, guys, if I don't teach you about the microbiology. But I can't teach you about either one if I don't explain to you how these cells are doing the things that they do differently. You understand? And that's why we had to go back to chapter 3. Alright? So you have the endogenous, which I showed you earlier, which is for viral and cell. And everything else is going to be exogenous. Means it's going to come in through some kind of receptor-mediated endocytosis, a phagosome, phagolysosome, blah, 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 this, that, the other. For a monocyte. For a B cell, it's slightly different. We'll talk about this. Because I said, remember, ignore B cell for a moment. Let's just talk about macrophages and how they do it. All macrophages will do this the same. You understand me, guys? So wait a minute. I thought about this. So what about the microglia that enter into the brain? You guys remember that? Remember there's a monocyte that before the blood-brain barrier gets sealed off, that these cells migrate into the neural tube, but they're not neural cells. They never came from the neural ectoderm. All right, there were monocytes that resided into the brain tissue and always stayed there. Well, guys, that's the link between immune and neural. That's how I looked at it. From the very first time I knew that, I had learned it. I said, oh, well, that's a link. That means neural and immune are linked? Yes. Then if you read August Scientific America, there's an article about how there are immune cells in the dura mater that are there dedicated solely to the purpose of making sure that the brain works properly. That is amazing. So if your brain goes bad, then can your immune system go haywire? And if your immune system goes haywire, could you have something go wrong with your brain? So we are really more intercommunicated, connected, and communicated than what we thought we were, huh? Yeah. Mm-hmm. So when my grandfather had a stroke, I always thought, so what was, he had the stroke, so I wonder what was the overall impact on his ability, his endocrine system, to truly be able to communicate with his immune system regularly. And I thought about this long before this article had ever come out. I said, well, it had to have gone haywire. So, these B cells now, let's talk about these B cells. So that MHC class, let me finish the MHC. So the MHC class 2 guys will be sitting right out here on the membrane with whatever one of those self-antigens that it decided that it wanted to put on there. It could put them all on different ones, each one presented it. Everybody see that? There's triangle. There's the Jewish star, and circle. All those will be MHC class 2 markers, guys, with exogenous antigen. You understand it? Exogenous antigen. Endogenous antigen of self and viral, MHC class 1. Everything else, MHC class 2. You got me, guys? They call that MHC class restriction. That idea that only endogenous peptides get processed and put on MHC class 1s versus exogenous protein, lipopolysaccharide, whatever protein, whatever's formed that's outside the body, that comes in, right, near the cell brings it in but never allows it to go in unless pathologically it has the ability to do so. Okay? And that's where you get into the nuances of medical microbiology, not microbiome. Because microbiome, you just talk about all bacteria. Medical microbiome, you only concern yourselves with about microorganisms that cause disease in humans. You understand? And there's a difference. Not all the bacteria that exist in the world causes disease in humans. One of them in particular, E. coli, like I told you, we're all shit eaters. Okay? Thank God for E. coli, because that's the one guy that sits in our GI tract regularly, and we need it. Yes?
That MH2 that you have on your.
MHC class 2, Mark.
Sorry.
Yes.
MHC.
No, just so that you know, so that when you look it up, you know it's MHC. So what does MHC stand for? Major histocompatibility complex is what it means, guys. Wait a minute. Major histocompatibility. What does that mean? It's involved with organ rejection. Does that make sense? Would that make sense, guys? Would you suspect that these are the receptors that are involved with organ rejection? Yes, right? Because they're the ones that are presenting self-antigen on. Yes? They're the ones that are presenting foreign antigen. Yes? This is the way in which we communicate. This is the way in which our cells communicate with the immune system. Okay? Any questions so far? Yes?
I remember I seen this thing where this lady, she got mauled by a chimpanzee or whatever, so she got a face transplant. And
She got a what?
she got a face
She got a pet chimpanzee.
yeah.
She got chewed up. Her face got all chewed up by a chimpanzee?
Yeah.
ripped off.
And then
Whose face did you put on?
You can give
I don't know, but
I don't
it said
know.
that her face, her body like rejected the face
Yes.
transplant. So that even it's the same thing.
Yeah.
Wait, what about
I can't just take somebody's skin and put it on somebody else, right? Because why? Because those self-antigens are different, right? So what winds up happening? There's two situations here. When you transplant, so let's go there for a moment because so when you transplant, let me erase good old DIC. Make sure you learn this. DIC, sepsis, DIC. All right? That's the one that, remember. All right. So, you have host and you have donor. The donor is giving the transplant. Okay? So, here's what happens. The transplant is considered to be grafted. So it's considered to be a graft. Okay? So one of two scenarios is going to happen, can happen, and will happen, unless you match your MHC class 1 and class 2s, guys. You hear me? This is the reason why. You got to match your MHC class 1s and class 2s. Because if I just transplant anybody's tissue onto somebody else, doesn't matter what tissue it is, the MHC class 1s and class 2s are still working for both. So you have to contend with, well, one, the donor is giving the graft to the host. So the host can have rejection to this. That's called host versus graft disease. The host is recognizing the graft as foreign because the MHC class 1 markers and the antigens that are being presented by these cells are being recognized by the immune system saying, hey, this is foreign, doesn't belong here, let's destroy it. You destroy the graft. The host destroys the graft. Did everybody hear me? Well, what happens if it's tissue that has some kind of lymphatic cells in it or immune cells in it? Huh? So you can get this. The graft versus host disease. This is where the graft with its immune cells are recognizing the host cells as being foreign and targeting them for destruction. So you can get any one of the two, if not both. You see that? So it's not just, that the body will reject. This is what they call the body rejects the organ. Right? When they take that graft, they put it in that body and it doesn't match. The body's going to destroy it. Now, you're lucky if the body just destroys it. You're really unlucky if the organ had immune cells that now get introduced to your body and now are stimulating your immune system to start destroying itself. You ever did? That's graft versus host disease. Very dangerous. Very dangerous. The host versus graft and graft versus host disease. You
So
can
how
look
could
this
they
up.
prevent that from happening? Do they have?
Suppression of the immune system. Sounds like a good idea? You need that. You need that graft. You need that organ. Otherwise you're gonna die.
But no, is there like a way to see if like the donor has kind of like the same? I don't know.
There is, absolutely. Yeah, that's the whole process of matching donor with the host. That's the whole idea. So that's why we go through this whole process of compatibility. And what are we looking at? We're looking at the major histocompatibility complexes. We're looking at the MHCs. And we're trying to, there are others, and there's multiples of MHC class 1 and MHC class 2. Yes.
Is that why stem cells is so important? Because it'll bypass all that?
Yeah, well, because
your
of their own stem cell, that's the idea of like everybody's saving their umbilical cord and then being able to get from the umbilical cord stem cells or blood stem cells in case you develop some kind of disease. But if it's a genetic condition, then those cells, guess what? They inherited that genetic condition, so, what good is it? So, it's not really they thought that was the next best thing. I mean, great if you have like more than one kid and they're genetically the same, because no kid is genetically the same unless they're monozygotic twins that came from one fertilization event. Right? Mom and dad got together, did whoopee, right? And there was one sperm at one egg, and that one egg, fertilized egg, split into two human beings. Right? Genetically identical, but with different fingerprints. Yes?
Host versus graft.
Host versus graft.
Graft. Rejects graft. Graft
That's
versus
right.
host does what?
It kills the host.
But
Yeah. So this results in destruction of the graft, right? In destruction of the transplant, destruction of transplant, right? So whatever organ was transplanted was destroyed. No big deal. This can kills host, or causes can cause inflammation in host.
But did you say that was only like if it had to do with something of the defects?
No, if there's if you don't do your compatibility right, if you don't match these two, you could get either one of these two, if not both, depending on what organ you're transplanting.
Oh.
You understand? Depending on what organ you're transplanting. All right, depending on what organ you're transplanting. Okay, any questions, guys? So you got SCID, right, which is SCID, severe combined immunodeficiency disease. You got the host versus graft disease. You got graft versus host disease. I did talk about hypergammaglobulinemia, which is nothing more than excess antibody in the blood plasma. Remember, we talked about that. If you have excess blood plasma protein, then it becomes thick and viscous. That's like SLE, systemic lupus, right? So there's indicators. When you have high levels of IgG in blood, when they're like excessively high, like way high, that's an indicator of a B-cell lymphoma. That's an indicator of a B-cell lymphoma. That's not the first time I mentioned that to you guys, right? So you can have B-cell lymphomas, T-cell lymphomas. You can have, you can have a lot of different stuff going on. So that excess IgG in blood is an indicator that you've got some kind of a B-cell lymphoma, and it's producing excess IgG in the body. So let's talk about the B-cell, because I talked a lot about the macrophage. and how its ability when it's and I'm opsonization, is it? Opsonization? It's O, with an O, right? Opsonization. So it's with an O, no. So opsonization. And phagocytosis via receptor-mediated endocytosis, that's for macrophages. I'm not going to tell you that receptor-mediated endocytosis doesn't occur with B cells. But what it does more so than anything else, which is really interesting, I'm going to erase this now, all right? So this is the monocyte more than anything. And we talk about B-cell lymphomas and host versus graft disease versus graft versus host disease. Oh, and exogenous thing. Now, let's go to just talk about the B cell for a moment. Because the B cell is very interesting. The B cell can actually turn on itself. I said about this before. And it can turn on others. Because it acts like macrophages or monocytes. In that it has an MHC class 2 marker capability. MHC class 2 allows exogenous proteins to be displayed. Did everybody hear? So the B cell, here's what happens. The B cell, separate of becoming, so I'm going to write it here. So separate of the B cell becoming a plasma cell. And the plasma cell becoming this antibody factory. Making IgA, IgD, IgE, IgG, and IgM. IgM being the biggest. IgA found in mucus as dimers. IgD, IgE, hypersensitivities. IgG found in the bloodstream. There's 4 different isotypes. This is the one that gets transferred via the placenta. IgM is big. It's large. It's a pentamer. IgG is a monomer in blood. So these two are only found in blood. This found in mucus. These found in hypersensitivity reactions. IgE specifically associated with histamine release and mast cell degranulation. Everybody follow? You should know that stuff. IgE. IgE is the antibody for mast cells. Okay? Specifically for the release of histamine. You need that cross-linking like I wrote on the board. So now let's talk about, so that's what the B cell does. Wow. Isn't that amazing? But separately of the B cell becoming a plasma cell and having antibody factory capability to make all these proteins that are soluble protein, soluble water protein, water-soluble protein. Separately, they have a B cell receptor. And that B cell receptor is nothing more than an antibody with +1 constant fragment. Everybody understand? So now we get to talk about the antibody in more precise terms. So we have a light chain. We have 2 light chains. And 2 heavy chains. Okay? Now, each heavy chain, so I'm going to use a different color. Each heavy chain has a constant region and a variable region. So this region, from here to here, is variable. And for the light chain, same thing. Variable. Same thing here. Variable. Same thing here. Any questions so far? That's a variable region. Then, each heavy and light chain constant region. Here and here. Here you'll have 1 constant region, 2nd constant region, and a 3rd constant region. Called the hinge region. Everybody see that? So here then, the light chains, I'm going to erase the constant, and I'm going to relabel this whole thing. I'm going to erase the variable. This crap. All right. So, any questions? So these are your variable regions. So we'll call this the VL, VH. Variable region of the heavy chain, variable region of the light chain. Variable region of the light chain, variable region of the heavy chain. Everybody follow? Because you got two heavy chains, two light chains. Each light chain and each heavy chain has their variable regions. Everybody understand? And the destiny of this protein that the variable regions be opposing each other, because it's there that the epitope, it's in these crevices that the epitope, it's in these crevices. That the epitopes of antigens are recognized. Did everybody hear me? It's in the variable regions of these antibodies that the epitopes of these antigens will be recognized. Did you go check out that book? Little thin book, says immunology on it. Look at it. Nice book, isn't it? A lot of information in that book. How many pages? Like 200 pages? And it's all colored.
Yeah, it's purple.
It's purple and red, reddish, kind of orange, and it's all illustrations, guys. And you go through and you can read. There's even more detailed information than what I'm giving you. I'm just giving you the skinny of it. There's a lot more to be had with this. There's a whole series of molecules that we're gonna get. I want to talk about some of them. So I got light chain, heavy chain. Everybody follow? Then I have what? I have a constant region for the light chain, each constant region for the light chain. But I have what? 3 constant regions for every heavy chain. Everybody see that? So I have what? A C1, H, C2, H, and a C3H. Everybody see that? What do I mean? C1, C2, C3. Don't confuse cervicals now. I'm talking about constant regions of the heavy chain. There's 1, 2, 3 constant regions of the heavy chain. That's with any one of these. IgA, IgD, IgE, IgG, IgM. Did everybody hear me? Whether they're monomers or pentamers or dimers, the antibody still has the same structure. Everybody hear me? However, the B cell receptor does not. Do you ever understand that? This is the antibody for what is secreted by the plasma cell into blood or into mucus. This is not the antibody that sits on the membrane of the cell. Did everybody hear me? I said, well, Professor P, man, come on, man, this is too much stuff. I said, no, it's not. Watch. What's the difference? What do you think the difference is, guys? Am I going to make some elaborate new antibody? Nah, what do you think I'm going to do? Everybody ready? Watch this. I'm going to add a 4th constant region to the heavy chain. That's it. When I add that 4th constant region to the heavy chain, it now makes it membrane bound. B cell receptor. Everybody see? So my B cell has I told you, didn't I tell you? That the B cell, 7 of becoming a plasma cell, has a B cell receptor. And that B cell receptor is an antibody with 1 extra fragment, a constant fragment. There it is right there. That 1 extra constant fragment on each heavy chain. And what that will do is allow the antibody to insert. So there's that extra, here's that, I'm gonna draw it in with. So there's the rest of it. Light chain, heavy chain. Everybody see that? But that's not the same. That's not the same. That's not the same antibody that's in the bloodstream. It's similar. It has variable regions. It's got constant regions, but it's got an extra constant region so it can be inserted into the membrane of the B cell. And then sure enough, guys, now watch. What will happen? If I recognize my antigen, what happens? Or what happens if that antigen is on the surface of the bacteria? you get receptor-mediated endocytosis. You everybody see that? So can a B cell then put this on, process it, and put it on MHC class 2? So can it act as a dendritic cell and turn on other dendritic cells to turn on B cells and T cells? Yes, it can. Did everybody see that? B cell's something special, baby. It's got a little macrophage activity, not quite like macrophage, but a little bit of macrophage activity. And it's got the antibody production that it can do. See that? So it can sit around waiting for the dendritic cell to stimulate it, or it can just stimulate itself. Now, isn't that a beautiful thing? Because what, guys? Because 10% of all the interstitial fluid that bathes every single cell, the entire organs, except for brain, gets reabsorbed back into the lymphatic system, and every lymph node, every B cell, every T cell, every dendritic cell is getting 10% of the sample all the time. Separately, 3/4 of the body is drained by the left lymphatic duct, and only 1/4 of the body, the upper part, is drained by the right lymphatic duct. And separately, lymphatic system absorbs fat-soluble vitamins along with cholesterol and dietary lipids, guys. Yeah, doesn't that make sense? Because look, wasn't I talking about teichoic acid and mycolic acid and lipopolysaccharide? They're lipid-based products, guys. So this is quite amazing because our lymphatic system is engineered to be sampling the lipid-based products of anything that's foreign. You got me? So from the GI, I'm gonna tell you we're all shit eaters, but that's all right. We got a lymphatic system. What? We got a mucosal associated lymphoid tissue that's specifically associated with the GI, and sampling this fat that's coming from what we absorb. Hey, you got any bacteria up in there? Are there LPS up in there? Any teichoic acid up in there? Any mycolic acid up in there? You see? It's an amazing thing, this engineering feat. Quite cool.